All right. So now that we've learned about graphs and graphing motion and how we visually represent motion, we also can utilize those graphs to come up with 4 or 5 equations that we can use to solve basically word problems related to kinematics. So these are called the kinematics equations. We're going to go over those today. So remember that if you're traveling at a constant speed, your position graph is a line. Speed or velocity, right? And if you are constantly accelerating, that it is a parabola. The slope of an xt graph is your velocity, and the slope of a velocity graph is your acceleration. And if you want to find the displacement, you find the area under the curve is your displacement, or your distance if you ignore the directions. And you just add the numbers. So let's look at that. Let's look at that acceleration graph. The generic position graph for something that's accelerating is a parabola. And the generic formula for a parabola is y equals a constant a t squared plus bt plus c. A, b, and c are constants. And when you do a quadratic curve fit, this is the generic equation. It turns out that if we were to replace the variables here, we would see that the final position at any time is equal to 1/2 of a, which is the acceleration of the object, plus t squared, plus the initial velocity of the object times t plus its initial position. A lot of times we put the positions over on one side, and we say that the change in position of an object is equal to its initial speed times time plus 1/2 of its acceleration times time. It's important for you to remember that these are vector quantities. So when we plug in for A's and for velocities and for positions, we're going to make sure that we plug in positives and negatives as needed. This is our first kinematics equation. It is basically the equation of the position graph for something accelerating. It's important for you to know that the kinematics equations only refer to something that is accelerating in time, not to something that is traveling at constant speed. If we look at the velocity graph for something that is accelerating, it is a constant line. And the generic formula for that line is y equals mx plus b. Well, y is the velocity at any time. The slope is the acceleration times time plus the initial velocity. So our next kinematics equation is just the velocity equation for a line. Vf equals vi plus at. Vf and vi and a are all vectors. So it turns out that we have 4 kinematics equations that we can use. The first 2 are from our graph that we've learned about for accelerated motion. Okay? And then the other 2 algebraically combine these in one way to form the new equation. So if you look at this, we've got Vf, Vi. Actually, let me redo this. We've got Vf, Vi, A, T, and our change in displacement. These are the 5 variables that we have. But if you look at these equations, each one is missing one. So there's no delta x in the first one. There's no VF in the second one. There's no T in the fourth one. We factored that out. And there's no A in the last one. So each one of these is missing. It only has 4 of the variables. So if you know any 3 of those, you can find the fourth one. So it's a powerful tool for us.